Chemical bonding, metallic bonding. In this tutorial, we will be going over what is metallic bonding, the electron-C model of metallic bonding, and the physical properties associated with metals. Metallic bonding. Metallic bonding is a third category of chemical bonding and is distinct from ionic and covalent bonding. So, for example, in ionic bonding, we might bring in a metal like lithium with one valence electron, and then bring in fluorine, a nonmetal with 7 valence electrons, and then click on those electrons to make them different, and then transfer lithium's valence electrons over to the fluorine atom to make fluorine an ion, and therefore an anion, and lithium now a positive ion or a cation, and the lithium and fluorine ions are held together by electrostatic forces. We've also talked about covalent bonding. So we might bring in the nonmetal hydrogen with 1 valence electron and chlorine with 7 valence electrons, and then we'll click on the hydrogen valence electron to make it different. Click on the hydrogen valence electron and one of the chlorine valence electrons, and then we can see the hydrogen and the chlorine coming together to form their full octets, or in hydrogen situation, a duet. Metallic bonding is different, as we'll look at more throughout this video. The electron-C model of metallic bonding. Metals have the tendency to lose electrons due to their relatively low ionization energy values, resulting in the formation of cations. The metal bond is the electrostatic attraction between positive and negative charges. Each metal atom shares its electrons with other atoms, resulting in a metallic crystal lattice structure. A metal structure can be thought of as cations of a metal element arranged in a regular pattern surrounded by a sea of delocalized, freely moving electrons. Here is an example. What we're going to be looking at here is metal atoms donating valence electrons to the sea of mobile electrons moving among the regular arrangement of cations. So we're just going to start with a simple aluminum can. And when we think about this aluminum can and we zoom in on it, we can see this Bohr model of the aluminum atom with its 3 valence electrons. As we move farther out, we can see the positive cations with a +3 charge and the delocalized electrons moving around those positive ions. As we move farther out, we can see how these atoms of metals are closely packed together as they are moving. Now we look at a piece of magnesium ribbon. As we zoom in, we can see the Bohr model of the magnesium atom with its 2 valence electrons. And as we zoom out and we see the positive cations with a 2+ charge and the 2 valence electrons that are delocalized and moving among the ions. Physical properties associated with metals. Metals conduct electricity in contrast to an ionic solid, where electrons are localized or fixed to an ion. The electrons in a metal are free to move. The movement of electrons in response to electric potential or voltage is an electric current. Metals are conductors of heat due to the mobile electrons assisting with the dispersion of heat throughout the metal. Malleability, the ability of a metal to be hammered into thin sheets, and ductility, the ability of a metal to be drawn into wires, can be accounted for by the electron-C model. Since electrons in a metallic crystal lattice are not localized to specific chemical bonds, the metal cations can slide past one another within the lattice structure, resulting in the formation of a new shape. So what did you learn in this tutorial? We answered the question, what is metallic bonding? We talked about the electron-C model of metallic bonding, and then finally, physical properties associated with metals. Need more help? Feel free to contact me. Have a great day.